Okay, this lesson is about discharging a capacitor. There will be obviously talk on how to charge a capacitor. That's a whole different lesson in itself, but let's just look at discharging a capacitor. Okay, we'll take our capacitor and we will discharge it through a resistor, and that will of course cause some current to flow. Obviously it has been charged previously, and across this capacitor there is a certain potential difference that's been achieved. And when we initially connect to the resistor, then what we definitely understand to start with is that the current is going to be the potential difference divided by the resistance of the resistor. And what I'm going to do is put that as I0, because that is the initial current. Now, as charge flows off the capacitor, therefore the differential has got smaller. The difference in charge has got smaller. So therefore, it's not going to as readily push the charge off. So essentially, what we're saying is that this initial value will start to decrease until it hits zero. Until, in other words, there is no longer a differential of charge between these two plates. So therefore, just to say, but we know that the voltage is decreasing as the capacitor discharges. Hence, the current changes. Okay, so what we need to do really is have a full, we want to work out the current at any time during this discharge. So what we're going to do is we're going to talk about, and this makes use of it, the mathematical term exponentiality. And what it means is this: if I have a large difference of charge from one side to the other side, then I'm going to have a large potential difference. It also suggests I'm going to get a large current flowing. As this decreases, so the current flowing will decrease itself because there's less of a differential. So what I'm trying to say is that the current is proportional to what you start off with. Or I can say the current is proportional to how much charge you start off with. In actual fact, the current is going to equal a constant with the amount of charge I start with. The larger the charge, the larger the current. The smaller the charge, the smaller the current. And we also know that the current is the rate of change of charge with respect to time. And because obviously this is current charge being removed, I'm going to have the minus sign in there. So in fact what we're saying is, and that is the definition of exponentiality. Okay then, so let's work that through mathematically now. You don't need to write down this proof, but you do need to have a knowledge of how we come from this point here, saying the amount coming off is proportional to what we start with. So let me try and write that down now a little bit more mathematical rigor. If I rearrange the equation, and I bring Q underneath the dQ, and I bring the dt up to the other side, then we have 1 over Q dQ, and I want to integrate these sides because I want to find out what happens over any period of time. So it could, obviously we go from 0 to an unknown time t, and we start with a known quantity, Q0, and then we're going to find out what the charge is after a certain time. If you're familiar with this integral here, you should know that should give you ln Q between our two values, and here of course minus t between our two values. And that gives rise to, well, let's put the limits in. So first we'll put in this limit and then minus the other limit, so that's ln Q minus and then Q naught. The first limit, which is t, and the second limit gives us nothing. And with a little bit of mathematical rearrangement, I know this is ln q over q naught minus beta t. And then how do we get rid of a natural log? We use an exponent. So if I e both sides, that gives me q over q naught. So here is our expression for how to work out how much charge you have over a period of time. It's going to be dependent on how much charge you start with, and then exponential function with regards to time. Okay, that's it's not just with capacitors. You'll notice this mathematical model. It happens with any radioactive decay as well. Let's just draw our graph of what it looks like. Exponentiality, as I'm sure you remember with GCSE radioactivity, means that you do have the same proportion drops over the same period of time. With radioactivity, we deal with half-life. Here, we'll deal with something just a little subtly different. But I hope you understand that as well that it's not just the charge, of course. The charge is proportional to the voltage. More charge differential gives you a higher voltage. More charge is also proportional to the current as well. So this exponential behavior could be the current or the voltage in any case. And also, I've drawn that very badly. What we should have probably done is say that it does start from a known point. Good. I'm just going to briefly write down as well what this beta factor is here. I'm going to use just a bit of very, very big generalizing maths. Let me take you back up to the top here and say, I know that Q, let's start with that point, I, is beta Q. I'm going to look for an expression for beta. Q is CV. We know that from our other relationship on capacitance. I also know that V is equal to IR. So what I could be writing is I equals beta CIR. Gives us 1. Beta is 1 over RC. So therefore, what I need to write down here is say that Q is Q naught e to the minus T over RC. In other words, the proportion by which it drops in regards to time is equal to this RC factor. RC is called the time constant. In order for this equation to hold true, Q and Q having the same dimensions on either side, this must be dimensionless. So that means R multiplied by C gives a units of time. That's really interesting because we were going to have a look at that a little bit more now. We're going to look at that graph, that exponential graph. And we're going to look again at that RC value. Let's say that we take our equation. What happens when T is equal to RC? What happens when we look to the time period, which is the same as RC? Well, what's going to happen to the equation is this. We're going to get e to the minus 1 because RC over RC gives us 1. And we know that's Q. If you plug it into the calculator, 0.368. So the charge, when you get to 0.0368, sorry, 0.368 of the initial charge, and that is RC, our time constant. And if we got to, a second RC, so if you want e to the minus 2, you're going to go for 2 RC. In other words, this is an eth of it. So rather than talking about half-lives and radioactivity, we talk about the RC time constant. So we talk about how much has come off in the time RC. Okay, one last mention of the graph, and then we'll do some problems here. Let me rewrite that equation. Now, when you're doing experiments, it's important to be able to work out whether this line is exponential. It could be 1 over x, could be 1 over x squared, you're not quite sure. So the line you're definitely sure of is a straight line. So when you're doing experiments, you're looking for straight lines with experiments. Or in the form y is mx plus c. Because then you can tell whether it sits on a straight line. So let's try and build an equation of a straight line with this. First of all, we take the logarithms of both sides, and hopefully know that multiples becomes additions and powers become multiples. And so therefore, this disappears because it's a natural log, and it comes down as being a multiple of e, which disappears, and it's an addition of 2. And then that's a minus in there. So we get minus t, 1 over rc, plus ln q naught. And if you can see, this is in the form of y equals mx plus c. Therefore, if we were to plot ln q against t, we would have something that's negative in gradient, starting at a point ln q naught, of which having a gradient of 1 over rc. So 1 you can work out whether it's exponential, and 2 you can work out the time constant from the gradient of that line. Good. Okay, let's quickly have a few problems then, to see how we get on. We're probably going to refer back to our equation. Let's take an ordinary circuit with a capacitor in it, going through a resistor, and that will cause a current. You often have to go through a resistor and use up the energy in the resistor. I'm going to use a 5 microfarad capacitor that has been charged to 12 volts, and I have a 2 megohm resistor. The first question first is, what is the RC time constant? Very simply, you multiply R and C together, bearing in mind you've got obviously scientific notation going on here. Micro is 10 to the minus 6, and mega is 10 to the 6, giving you 10 seconds. So in the period of 10 seconds, you will notice the graph dropping. So of the charge happening here, initially starting with, you'll get 0.36 of that charge occurring after 10 seconds, or an eth of that, if you like. Okay then, 2. What's the initial charge? Well, what can we say is we can say that Q is CV, so the voltage that I've charged it to multiplied by the capacitance, 5 times 10 to the minus 6 is my capacitance, and I've got 12 volt charge across, 12 volts of charge across it, and that gives me 6 times 10 to the minus 5 coulombs present. Okay, initially I'm going to get a current flowing based on the initial voltage, but then obviously the voltage starts to decrease as more charge flows off. So how long will it be, or let's ask another thing, how much current will be flowing after 5 seconds? So what's the current after 5 seconds? Okay, well, we're going to make use of this idea. I is I naught e to the minus t over rc. Remember, I can replace the q's and the v's, and the q naughts and the v naughts and the I naughts and the i's quite happily interchange them. obviously suggests, first of all, what's my initial current? Well, initial current is voltage divided by the resistance. 12 over 2 mega ohms gives me 6 times 10 to the minus 6 amps, a tiny current. So that's initially what's flowing out. At 5 seconds, of course, then I have the initial current, but an exponential factor of that, 5 seconds of my RC time constant. Well, we know that RC is 10 seconds, so really I'm e to the minus 2, sorry, a half. Because 5 over RC gives me a half, which gives me 6 times 10 to the minus 6, e to the minus a half, and then e to the minus a half will give me, I'm just going to double check on the calculator, so minus 0.5, hear that? Double check on the calculator, e to minus 0.5. Gives me 0.606. 6 times 10 to the minus 6 by 606 gives me 3.6 times 10 to the minus 6 amps. Okay, so that's essentially what happens, and there's plenty of questions for us to tackle. Probably not enough time for me to put another one on, but essentially if you're happy with how to, you do not need to be able to derive, but if you're happy with how this is achieved, understanding that the charge initially dictates how much flows off, and that's how that's dictated. You're happy with what the time constant means, and you're happy with how this equation works out, and then you've used it once or twice, then you should be ready for some questions. Okay, that's it.